Hello everyone, this is Mr. Los. Welcome to another exciting edition of HL Chemistry Flipped Classroom. We're here to talk about kinetics, collision theory, and really introduce you to the idea of chemical kinetics. And so thank you for watching, and let's get started. Now, this is the distance learning time when I'm making this. I'm having to make these videos at a fast and furious pace. I don't know that they're the quality that I normally, the quality that I normally would like, but we'll just do the best we can here. So, collision theory. So, in the distance learning environment, I had you watch that fun little video about prom date formation, and we talked about the students, or they talked about the students colliding with enough force to drop their books. It's a great analogy for chemical reactions. Collision theory basically says a couple things. Molecules are actual little objects. It's kind of sometimes hard for us to wrap our brain around that, but they do actually have to collide with each other and touch each other to have a chemical reaction. But even more than that, they must collide with each other for enough force to overcome the activation energy. That's something we're going to talk about more and more as we go here through this process. And they also must collide in the correct orientation. So not every collision necessarily is going to produce a chemical reaction. They might either collide too slowly, or they might not be facing the right direction. Like, for instance, maybe the carbon has to be facing this little thingy over here and not the oxygen. But if everything lines up, if they collide with the right orientation and with enough activation energy, we can get a chemical reaction. So that's the two major pieces of collision theory. So activation energy, I talk to you all the time about how precisely IB wants to have you be with definitions. This is one of those definitions. Activation energy is the minimum energy with which two molecules must collide in order to produce a reaction. For example, if you left off that word minimum on your definition on IB exam or an exam you take in this class, you would get that counted wrong. I want to understand, some people think that activation energy somehow changes. Unless we're talking about a catalyst being involved or something, activation energy is something that's constant for a particular chemical reaction. Every chemical reaction is going to have a certain activation energy. And for the most part, that's not going to be influenced by anything else, except a catalyst is definitely a major exception to that. So let's talk about some specific things that can influence the reaction rate. Basically, there's a couple of things you can do. You can either increase the number of collisions in a given time period, because that's just going to increase the likelihood of a successful collision. There's just going to be a greater number in a given time period. They're going to have the right orientation or the right energy, and we're going to make the reaction go faster. Or you could increase the average kinetic energy of those collisions, and therefore more of those collisions will be able to overcome the activation energy. A third thing you do, I guess, would be to lessen the activation energy, and that would require a catalyst. But those are the three major things you can do to increase or, make the reaction go faster. And obviously you can make it go slower by doing the opposite. So all of these things that I'm going to mention right now are specific things that are going to do one of those things that we just mentioned. Temperature is a huge one. Temperature affects reaction rate. Now, when we make the temperature higher, what that does is that increases both the energy and the frequency of collisions, because remember, temperature is proportional to average kinetic energy. So if we run a reaction at a higher temperature, all the molecules are moving faster, so there's going to be more collisions just because everybody's bouncing off of each other a little more frequently. But also, on average, those collisions are going to be more energetic. So temperature can make a pretty big difference in rate of reaction. There's a little rule of thumb that every 10 degrees Celsius about doubles the rate of reaction. So it can have a pretty big effect. Concentration also. When you think about, let's say, a 1 molar solution versus a 2 molar solution, there's simply, in the 2 molar solution, there's twice as many molecules, atoms, particles, whatever, in a given area. So there's going to be more frequent collisions. If we're holding temperature constant, the average kinetic energy of the collisions is not affected, but the collisions will be more frequent. So more of them will have the right orientation. Just law of averages, more of them will have the right orientation, more of them will have the right energy. Particle size. So this affects a solid. If you were to, let's say, think of a log, okay, like a giant log that if you try to start it on fire, like if you ever try to start a campfire with a giant log, you really can't do it unless you dump some gasoline on it. Instead, what you do is you split that log into a bunch of small twigs, or you use a bunch of small twigs to begin with. You light the small twigs on fire, those get started, you can light the larger thing on fire. Basically, the more pieces something is in, the more surface area it has, the more exposure it has to the things that it's going to react with, and the faster a reaction will happen. So with solids, you want smaller particles, which actually results in greater overall surface area. And then the last thing is a catalyst. So again, a catalyst is something when you define and think about very carefully. A catalyst is a chemical reagent that or agent that speeds up a reaction while itself not permanently changing. So it is not considered a reactant or a product. It might undergo some changes. In fact, often it might undergo some changes during the reaction, but those changes will always be reversed by the time the reaction's over. It usually provides an alternative pathway with a lesser activation energy, so that's why it's going to increase the reaction rate. Depending on what we're talking about, if it's like a biological catalyst, it might be basically holding molecules in place, so it kind of helps them achieve the right orientation, you could say. But by one of those two means, the top one is usually more for inorganic catalysts, and then the bottom one would be more often, although not always, for catalysts that are in living things. So we have talked a little bit about what are called Maxwell-Boltzmann distributions. So what you're seeing here is the same sample of gas, let's say, at 3 different temperatures, 0 Celsius, 1,000, and 2,000 Celsius. Now, in any given situation, it's a bell curve, so it's like, height of people or something. You got some short people, you got some tall people, you got some people in the middle. Well, in a 0 degree sample of gas, you've got some particles with less kinetic energy, some with greater kinetic energy, but most of them have this average kinetic energy, which kind of corresponds to 0 Celsius. As you heat a gas up, what happens is it gains kinetic energy, so that's why the 1,000 is shifted over to the right on the x-axis, but also the molecules start moving more chaotically and kind of bouncing off of each other, and it increases the standard deviation, you could say. So we get a greater spread. And so notice this is the same sample of gas. You could calculate the number of molecules by finding the area under the curve. So at 1,000 degrees Celsius, the graph has spread out and become wider. The area under the curve has to remain the same, though, because it's the same sample of gas. That's why it's lower. So this is a greater temperature, and this is an even greater temperature. Some people get a little confused. They think, oh, this must be a lesser temperature because it's lower down. That's not the case, where the farther to the right on the x-axis is going to be the higher temperature. So yeah, we had talked about that a little bit before, but now we're going to apply it to the idea of reaction kinetics. So one of the things that IB wants you to do is think about these Maxwell-Boltzmann distributions and use them to explain, for example, why a reaction would go faster at a higher temperature. So here we have two samples of gas, or two whatever, at T1 and T2. T2 is the higher temperature. Let's say that the activation energy, so remember temperature is really just, it's a way of measuring kinetic energy pretty much. Let's say this amount of kinetic energy is the energy with which they need to collide to produce a reaction. So therefore, any molecules that have less energy than that are not moving energetically enough to produce a chemical reaction. So at T1, this is the activation energy right here, and if we can see the original T1 curve that's kind of marked by the X hash marks here, those molecules right there are the only ones that have enough energy to initiate a reaction. All the rest of them are moving too slowly. However, at T2, so we take this same sample of gas, we heat it up. It shifts its whole curve over to the right. Activation energy remains constant because that doesn't change. Now, many more molecules, if we think about area under the curve, all of these molecules have enough kinetic energy to initiate this reaction. So moving it over, and again, there's more molecules, they're moving faster, they're harder collisions. And I think that probably kind of makes sense, that it's going to make the reaction go faster if the molecules have more energy. But this is just kind of tying it to the graph and tying it to the Maxwell-Boltzmann distribution. So another context with which we want to look at this is a catalyst. So here we have another Maxwell-Boltzmann distribution, and then we have some reacting gas or whatever. So this is the activation energy right here when the reaction is catalyzed. This is the activation energy, this is the uncatalyzed activation energy. And then if we add a catalyst, it makes the activation energy less, okay? So if the activation energy is right here normally without a catalyst, and this area under the curve represents the number of molecules that are going to be energetic enough, in the green here, in the uncatalyzed reaction, only these molecules right here in the green have enough activation energy. The rest do not. And they are moving too slowly. They are lacking enough energy to initiate reaction. But we add a catalyst, let's say, so that lowers the activation energy, and that moves the activation energy right here. So that gives us a bunch of additional molecules that have enough energy to undergo the reaction, and that is going to make this reaction speed up. So again, yes, catalysts speed up a reaction by lowering activation energy. I think that's relatively easy to wrap our brain around. But now we're doing something that's a little more challenging, which is applying it to this graph. So when it comes to reaction rates, I mean, you can say it, oh, this reaction is going faster, this reaction is going slower, but how could we measure it? It's actually a trickier piece of business than you might think. We need to be able to measure one of the, basically, we need to measure one of the reactants or products, and I'll talk more about it, but it's a little bit of a difficult task. Normally what we try to do is track concentration over time. That's ideally the case. So the standard unit is mole per cubic decimeter per second, which just means change in concentration over time, although you could use other units depending on exactly what you're doing. So it's the change in the concentration over time. But by the way, if you're asked for a rate unit, that's the one that you want to use. That's kind of the standard one. Just generically, if you're asked for a rate unit, that's the one that you want to use. So basically, you can define a reaction rate in a couple ways. Again, the tricky part is like figuring out what you're going to measure and what you're going to track. You can either measure it by an increase of the concentration of some product, sometimes referred to as the appearance of a product, or a decrease in the concentration of a reactant, because reactant concentrations go down over time. Either way, even though technically, since a reactant concentration is decreasing, that would technically be a negative, but by convention, we treat all rates as positive. And furthermore, reaction rates will be in proportion to the mole ratio, which is something we'll talk about more in just a second. And then just to reiterate and make this point clear, some people this is obvious, but just to make absolutely sure and make sure that it's written down there. As reactions go on, concentration of reactants go down and concentration of products go up. When we're looking at this more graphically a little bit later, that's definitely something that we want to keep in mind. So, and by the way, before I talk about this, the amount of all these things that you're writing down and these notes that you're taking, these notes are for you. You should write down as much as you think you need to write down. Do you need to write down all of this stuff, like this question and all of this stuff? I don't know. I don't think so. But what I want you to think about here is it says, how does the rate of NO2 production compare to the rate of O2 production? Notice it's saying the word production because they're both products and they're being produced. How will the rate at which O2 appears compare to the rate at which into O2 disappears? It's saying that because this is a decomposition reaction. It's saying disappears because this is the product and it is going to be disappearing over time. It's going to be turning into these products. So the concentration of this is going down, the concentration of these are going up. So the answer to both of these questions involves the mole ratio. All of these rates, by kind of definition or just by the necessity of stoichiometry, are always going to go right in line with the mole ratio. So in other words, how will the rate of NO2 production compare to the rate of O2 production? Notice the ratio is 4 to 1. So NO2 is going to be produced at 4 times the rate that oxygen is because of the 4 to 1 mole ratio there. How will the rate at which O2 appears compared to the rate at which into O2 disappears? The ratio is 2 to 1. So although this will be disappearing and its concentration is going down and oxygen's appearing and its concentration is going to go up, into O2 is going to disappear at twice the rate that O2 appears. Because this is a reactant, its concentration is going down. This is a product, its concentration is going up. Let me show you this graphically right here. So this is concentration here on the y-axis. It's molarity, but of course in the IB world we call that mole per cubic decimeter. And this is time. So a couple things to notice about this. The slope equals the rate in this type of graph, because slope is rise over run, right? Reaction rates are measured in change in concentration over time, so the concentration is the y-axis, the time is the x-axis, so the slope at any point of this is the rate. And we can notice that the NO2 is going up, we can notice that the O2 is going up. And if we were to measure the slope at any given point in this entire thing until they completely flatten out and the reaction stops or is at equilibrium, the slope of the N2O2 graph, if they made this graph properly, the slope of the N2O graph should always be 4 times the slope of the oxygen graph. N2O5 being a reactant, its concentration is going down and it's decreasing over time. And if we were to compare the slope of this, its slope should compare right along with the other ones, except negative. So, for example, O2 compared to N2O5, N2O5 is going to be disappearing at twice the rate at which O2 is appearing. So at any given moment, if we were to find the slope of the line, N2O2's slope should be twice as big, except negative, as oxygen's. So, as I was alluding to earlier, you can't just look at any old chemical reaction and say, okay, get it started and find the rate. For one thing, some chemical reactions are very, very fast, like almost instantaneous, and you really can't find the rate of those. But even ones that go a little slower, it's not necessarily an easy task. You have to have something that is measurable and a way to measure that thing. It's not so easy. So there's some options if the reaction produces, and by the way, you should be aware of these options and be able to think about rate experiments. It's going to be much more difficult, I got to admit, in this distance learning environment. Normally we do a lot of experimentation here, hands-on experimentation, so I don't know, we're going to have to think about it a little bit differently. But one thing you could do is if a reaction produced a gas, you could collect and measure that gas over a given time. That would be one way to find a rate. If a reaction undergoes some kind of color change, I'm at least going to show you some pictures of examples of some of these things in just a second, but if there's some kind of color change that happens, you could track that. That would be a way to do it. If the reactant is a solid and you could see it, you could make sure it was a limiting reactant and make sure it like disappears, so you could time how long it takes for the solid reactant to disappear. If you had a pH meter, and we're going to talk about pH later, when we talk about acid base, but perhaps you could track the pH changes over time, or timing until a solution becomes opaque due to a precipitate. And I'll show you an example of that. So just to give you a little bit of an idea of what I'm talking about. So like a class experiment is to do magnesium and HCl and to do some rate experiments with that. So what you're seeing here is a piece of magnesium ribbon that has been placed in a few different test tubes. And you can see the magnesium ribbon right there. It's bubbling away. It's producing hydrogen gas. So you can see the hydrogen gas. So you could, for instance, just time this reaction until the magnesium is totally dissolved or that you can no longer see it. And that would just be one way, like I mentioned. And I'm just trying to show you this to give you a little bit of a feel for what I'm talking about. Another thing, and again, like writing down this entire reaction, all that, I'm more just trying to show you some general examples here. Another classic reaction study in kinetics is the reaction between sodium thiosulfate and HCl. This is an example of using the appearance of a precipitate. When you do this chemical reaction, it makes sulfur as a precipitate. So you could start the chemical reaction, you could time it. So I start the stopwatch right now, and I drew this X on a piece of paper. And by definition, I'm going to stop the timer when I can no longer see that X. So we're timing. Ooh, boom, stop right there. So that gives us a way to track this reaction, time it, and then we could do some experiments, like we could heat it up, we could change the concentration, all that, and see how long it affected the time it took for that X to disappear. So a way to track the rate like that. A third example, or another example I mentioned, was color changes. Some reactions have color changes that reaction also kind of has a color change, but it's a little bit slower. So you wouldn't want to use just the color change, but we wanted to find a certain point of the color change. Some reactions have really nice quick cut, like this one. Very classic, again, reaction, chemical kinetics. There's a pretty clear stopping point here where the reaction turns black. So we could use that black color change as the way to time the rate of this reaction, called the iodine clock reaction. So as far as calculating reaction rates, one thing I want to just say before now is that one thing that's definitely true of almost all reactions, there are some exceptions to this for various reasons, but generally speaking, reactions slow down as they proceed. And can we explain that via collision theory? So think about that for a second. The reason that reactions slow down as they go, for the most part, is because, again, thinking back to what we mentioned earlier, the concentration of reactants is decreasing over time. And as we've discussed, the lower the concentration, the slower the rate, the fewer collisions there are going to be in a given time period. So as the concentration of reactants go down over time, so will the rate of the reaction. So basically, the rate's decreasing because the concentration of the reactants decrease over time. So rates of chemical reactions, again, with some very rare exceptions, are not constant. They start fast and they slow. So that brings up a couple of terms here that we need to think about very carefully. Since the rate is not constant, the rate's always changing, we speak about the instantaneous rate, which is the rate of a reaction at one particular moment in time. But then we could also talk about the average rate, which is the rate of a reaction at anything other than just an instant. So the average rate is the rate over time. Now, average rate is change in concentration over change in time, always made positive. So we can use that little expression to find the rate of a reaction. Now, I don't remember, in this group, if I've really talked about my friend Sam Jackson here, but sometimes I want to bring him out to help me make a point. People get a little confused. They see the word average and they want to add a bunch of numbers together and divide by the number of numbers. That's not what this is. The reason you say average rate is because the rate's not constant. So if you're looking at the rate over 10 seconds, you can't say this is the rate over 10 seconds because the rate's not constant over those 10 seconds. It's changing. So if at some point in this class you're asked to find the average rate and you find yourself adding up a bunch of numbers and dividing, you are definitely doing it wrong. And I want you to think of Sam Jackson's scary face here to hopefully remind you that average rate just means the fact that the rate is not constant. So here's a little bit of what I'm talking about, okay? And again, as far as whether you're going to write this all down, I don't know. There's practice in your workbook. But suppose we were somehow tracking the concentration of some reactant over time. I can tell it's a reactant because the concentration is going down over various amount of seconds. So it says, what is the average rate of this reaction over the first 20 seconds, over the first 10 seconds, over the second 10 seconds? So we're looking at change in concentration over change in time. And so it says, what is the average rate over the first 20 seconds? So that would be basically all of it. And so we're going to do change in concentration over change in time. Now with any kind of delta, technically we should be doing final minus initial. So it would be 0.1 minus 0.5, which is negative 0.4. But we said we were going to make it positive because rates are always considered positive. And the change in seconds is 20 seconds. 20 minus 0, 20. So basically it's 0.4 divided by 20. 0.4 divided by 20 is 0.02. And sig figs, I guess we'll keep this. And the unit is mole per cubic decimeter per second. And again, that's called an average rate. I'm not adding up these numbers and I'm not averaging anything. The reason it's called an average rate is because the rate's not constant over 20 seconds. So it's not the rate over 20 seconds, it's the average rate. So that's the first question, 0.02. Over the first 10 seconds, so now I just want to look at the rate in the first 10 seconds of the reaction. Now we should be expecting it to be faster because reactions start fast and they slow down. So change in concentration over time over this time period, 0.2 minus 0.5, that's 0.3. And then now the time interval is only 10 seconds. I don't know why I'm doing that. So 0.3 divided by 10 is 0.0300 mole per cubic decimeter per second, right at the non-fraction form there. So in the first 10 seconds, the concentration decreased by 0.3. It did it in seconds, so that's 0.03 mole per cubic decimeter per second. This last question here is asking me to look at this time interval. So notice the concentration is going from 0.2 to 0.1. So the change in concentration is 0.1. The time interval is 10 seconds, so that's 0.01. So in the first 10 seconds, our rate was 0.03. In the second 10 seconds, it was 0.01, and then overall, it was 0.02. That's when you look at the whole 20-second span. And again, called average rates because those rates aren't constant. And we could slice it up into smaller and smaller bits of time, but it would still be an average rate. Now, you could find an instantaneous rate, like what is the rate at one particular instant, and the way that you can do that is by plotting a concentration versus time graph. And you draw a tangent line and find the slope of that line. So, this next graph will show you what I'm talking about here. So, a tangent, you'll recall, is something that touches a point at one line. So here we have a concentration time graph. The thing is slowing down over time, but let's say I want to know what the rate is right at whatever that is, 7 seconds or whatever. So I find 7 seconds, and remember, the slope is the rate at any given moment. The slope starts high because it's fast at the beginning, and it slows down. So I want to know the slope right at that point. So the problem with that is you can't find the slope of a single point. You can't do that, but what you can do is you could draw a tangent line, and so that's what we're doing with this little triangle thingy here, is we're drawing a tangent line where at 7 seconds or whatever it touches this curve at one point. We draw a tangent line, and then we can find the slope of that line, and that would be the instantaneous rate exactly at 5 seconds, how fast the reaction's going, exactly, or 7 seconds or whatever this is, exactly at 7 seconds. All right, thank you so much for watching. I hope you're doing as best as possible out here in the distance learning. I know I packed a lot of information here into this. Please contact me with any questions, and I hope you have a great rest of your day. Thank you.